Welcome back. So here are the two examples I asked you to complete on your own. I've highlighted the parts of the function, including the initial amount and the growth or decay factor. So on C, this is a decay function. The initial amount is 400. The decay factor is 0.925. The decay rate, I'm going to go back over this really quickly one more time. It's a decay, so it's 1 minus r. So 1 minus r equals 0.925. I'm going to convert the 1 and the 0.925 to percentages, so that's 100 minus r equals 92.5%. I'm going to add r to the other side of the equation to make it positive, and I'm going to subtract 92.5 from 100. So r is over here and it is now positive, and 100 minus 92.5 is 7.5%. So 7.5%. That's given as a percent because I converted to percents my 1 to 100 and my 0.0925 to 92.5. So that's why this is a percent. If I wanted to write it back to decimal form, I would take my 7.5% and I would bump the decimal back 2 places, and that would be 0.075 in decimal form. The next one is a growth function. The initial amount is 2,500. The growth factor is 1.2, and the growth rate, so that's going to be 1 plus r because it's growing, equals 1.2. So 100 plus r equals 120. So 100 plus some rate gives you 20. So that's 20%, or 0.2 in a decimal. All right, let's check out some word problems involving growth and decay. So this first one, the original value of a painting is $1,400, and the value increases by 9% each year. Write an exponential function to model the situation, then find the value of the painting in 9 years. So we're going to identify the important parts of the function, and we'll start with the initial value. The original value of the painting is $1,400. So that's our starting value. The value increases by 9% each year. So that's our rate. So 9%. We'll take and convert to decimal. 1, 2. So that'll put a 0 in front, and that'll be 0.09. Write an exponential growth model. So a model means that we'll write a function that could represent any x and y pair for this situation. So it'll be in the format of y equals a times b to the x. But in the place of b, or instead of b, we will write 1 plus r because it's a growth function. So here, our base will be represented by 1 plus r. So that'll be y equals, we'll substitute our initial value of 1,400 here, and 1 plus 0.09 here for our rate. And then instead of x, we'll use t for time. And then we'll go ahead and add the base value together to get y equals 1,400 times 1.09 to the t. So this function represents the growth of the value of this painting over time. And we could find the value of the painting by substituting any amount of years for t, and that would give us the resulting value after that amount of time has passed. Now, this is a function that models the situation because it has two variables. It has the independent variable of time, and then it has the dependent variable, which in this case represents the value of the painting. So if we're asked to write a function to model the situation, it needs to have both variables still in the equation. Then we will evaluate this for the given amount of time, which is 25 years, and that'll give us the current value after 25 years. So y equals 1400 times 1.09 to the 25, and you can just substitute these values into your calculator to get the resulting value, which is $12,072.31. Let's try another one. In example 3, the population of a town is decreasing at a rate of 1% per year. In 2000, there were 1,300 people. Write an exponential decay function to model the situation and find the population in 2008. So this is a decay function because the population is decreasing. So it's decreasing at a rate of 1% per year. So our R value is 1%. So we want to convert that to a decimal, 1%. Think about these little zeros on your percent symbol as being the two decimal places that you're going to move to convert it to a decimal. So that's 0.01. And the starting value in 2000 is 1,300. So keep in mind that 2000 is year 0 for this situation. So 1,300 is our initial value. And we'll write our function, and this is a decay function, so it's going to be 1 minus r. So y equals initial value, which is 1,300, times 1 minus r, which is 0.01, to the t. Again, the function to represent this situation will have both variables, the t and the y. We'll go ahead and combine like terms here to get y equals 1,300 times 0.99 to the t. Now we're ready to evaluate for the given amount of time. So we're asked to find the population in 2008. So if year 0 was 2000, then 8 years have passed. We can evaluate the function for the given time, 8 years, by substituting t here. We can also use our graphing calculator or multi-view calculator to find a table and scroll to the 8 in the table. So first, I'll substitute into my calculator. And I'll substitute it on paper as well. Y equals 1,300 times 0.99 to the 8. And that gives me 1199.6 people. 1199.6. But we can't have 0.6 people, so we'll round that to 1,200 people. So we can take this function, this entire, function that we wrote here, and substitute this into our calculator into y equals, or our table creating function in our calculator, and then scroll to year 8 in the table. So you want to make sure when you do that, you type it in for y equals and keep this as a variable t, and then you can see how the population grows from year to year, and then you could scroll to whatever year you're looking for and find the value at that point in time. In example 4, the cost of tuition at a college is $12,000, so our initial value is $12,000. It is increasing at a rate of 6% per year, so that will be 6%. as a decimal will be 0.06 for our rate. Find the cost of tuition after 4 years. So our time is 4 years. So our function will be y equals 12,000 times 1 plus 0.06 plus, because it's growth. And we were not asked to write a specific function. We can just go ahead and evaluate for 4 years. So 1,200 times 1.06 to the 4. Plug that into your calculator, and I really encourage you to practice along with me using your calculator correctly, because oftentimes students can substitute the values into the equation correctly, but then they make errors when they input it into their calculator and get the final answer wrong. So the final answer, the cost of tuition after 4 years, is $15,149.72. Let's try one more on this page. The value of a car is $18,000. So that's our initial value, $18,000. And it is depreciating. Depreciating means that the value is going down, and the rate that the value is going down is 12% per year. So we'll convert that to our decimal, so 12%, 12, is 0.12. How much will the car be worth after 10 years? So 10 years is our time. So our equation will be y equals 18,000 times 1 minus, because it's depreciating, so it's a decay function, 0.12 to the 10th. So that'll be 18,000 times 0.88 to the 10th. Plug those values into your calculator, and that gives us a 10-year later value of $5,013.02 for our car. One cool thing that I'd like to note here is just that if the value is decreasing by 12% in a year, then that means that 88% of the value is left. And even though 88% is a significant amount, like if you got an 88% on a quiz or a test, you might be feeling pretty good about it. But because it's less than 100%, it means that the value of the car is decreasing or depreciating over time. Now you're ready to practice on page 4 and page 6 of your packet. Reach out if you need help. Good luck!